Hello everyone, I am Dr. Naresh Kumar, Assistant Professor from the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on question bank discussion on power switching devices. So now here we have total 20 questions in the first module. So power switching devices. So now first demonstrate and different modes of thyristor SCR with the help of its static VI characteristics. So first there are three modes. So first mode is a forward blocking mode, and next second one is a forward conducting mode, and next last one is a reverse blocking mode. So first reverse blocking mode I will explain. So first here when negative terminal of the battery is connected, this is the circuit structure of SCR. So now here negative terminal of the battery is connected to the anode and positive terminal of the battery is connected to the cathode. So now here negative, in this case J1 and J3 junctions are in reverse bias, and next J2 junction is in forward bias. So now here a small amount of leakage current flows through from anode to the cathode. Here J1 and J3 junctions are in reverse bias and J2 is in forward bias. So there is no current means small amount of leakage current. So small amount of leakage current will flow. So when this voltage is increases certain values, J3 and J1 junction will be avalanches this J1 and J3, and next huge amount of current flows through from anode to the cathode. So that I will explain in the static VI characteristics. So now in the second mode is so now here let me change the color over here. So now here is a when positive terminal of the battery is connected to the anode and negative terminal of the battery is connected to the cathode, and J1 and J3 junctions are in forward bias and J2 junction is in reverse bias. So here we are not giving Ig is equals 0. Here is also Ig is equals to 0. So now here there is a few amount of current. Here anode current is in microamperes in reverse blocking mode, but here in this case so anode current in milliamperes. So now here small amount of current flows from anode to the cathode, but here when it will conduct SCR, here J1 and J3 junctions are in reverse bias, forward bias, and J2 is in reverse bias. So when you give the so now next case here when you give the gate current, Ig is not equals to 0. Ig is greater than 0 means here we are giving the gate pulse, positive gate pulse to this one, plus and minus. So that is Vg. So now here if you give the gate pulse, positive gate pulse to this junction, this gate, and here J2 junction is. So now here J1, J2 and J3. All junctions are in forward bias and current flows from anode to the cathode. In this way, SCR will conduct. So here in the static characteristics are here. So this is the forward blocking. Let me change the color over here. So this is the forward blocking mode. So now here it is a forward conducting mode. Here is the reverse blocking mode. So now here how it will work. So when anode is positive with respect to the cathode, J1, J3 are in reverse bias. J2 is junction is in forward bias. Only small amount of current, milliamps current flows from anode to the cathode. So when you give the gate pulse, here greater than this 0. So now here the SCR is going to the forward conduction mode, means when you increase the gate current, so now here SCR conduction is possible as earlier possible. So here like this. So now it will come, it is coming to the when latching current, when it is reaches to the latching current, SCR is going SCR will go into from forward blocking mode to forward conducting mode. That is the case here when negative terminal of the battery is connected to the anode and positive terminal of the battery is connected to the cathode. So here, so J2 and J1 and J3 junctions are in reverse bias and J2 junction is in forward bias. So now here a microamperes current flows from anode to the cathode. So now here when that supply voltage increases, this reverse breakdown voltage, so J1 J3 junctions are avalanches and huge amount of current flows through this one. So that is independent of this supply voltage. So now here these are the cases: forward blocking mode, forward conducting mode, and reverse blocking mode. So now this is the case for this question. And next, second question is explain basic structure, operation, turn on and turn off characteristics of SCR. So now here operation we have already studied in the previous question. And next, what about the structure? It is what is the structure here? It is having three terminals, anode, cathode and gate. So now here how many layers here? Layers are here 4 layers. So first one is a PN, alternate PN layer. So if you see this diagram, so now here P plus layer, N minus layer, P layer and N plus layer. Here plus indicates the heavily doped layer, minus indicates the lightly doped layer. Here no sign indicates the moderately doped layer, and N plus, here N plus indicates plus heavily doped layer. So here 4 layers. So here this layer width is 10, this level of doping is 10 raised to the 19 per centimeter cube, and now here this width is 10. P plus layer level of doping, and next this is the level of doping, and next this one is a thickness. This one is a thickness of P plus layer, and next this is the N minus layer, 10 raised to the 14 per centimeter cube. This layer is depending upon the supply voltage, and next this is the this width is depending upon the breakdown voltage, and now here this is a moderately doped layer, 10 raised to the 17 per centimeter cube, so 250 to 300 micrometer, and next this is the 10 raised to the 19 per centimeter cube. This is the 250 to 300 micrometers. This is the anode, this is one is a cathode, and this one is a cathode and this one is a gate. And anode is connected to the P plus layer, and N plus layer and cathode are connected, and gate is connected to P layer. So now here if you see operation already we have studied. So here this is a J1 junction, J2 junction, again J3 junction. So 3 junctions, 4 layers, J1, J2, J3. Now here if you see the characteristics of SCR, so now here turn on characteristics and turn off characteristics. So turn on characteristics, here we have total 3 times. So delay time, rise time and spread time. So here in the turn off time, so here TRR, reverse recovery time and gate recovery time. So that 5 times I will explain. So first here from the gate current, from the anode current, from the anode voltage I will explain. So first gate current, from the delay time I will explain first. From the gate current, from the 0.9 90% of gate current to the 100% of gate current. So that is here, this is the case. So now here from the 90% of, this is the delay time, from the 90% of gate current to the 100% of gate currents. So that is the delay time. So in another way, from the anode voltage, from the 100 percentage to 90 percentage, from the 100 percentage to 90 percentage. So this time is the delay time. From the leakage current, I will explain. From the leakage current to 10% of anode current, that is the delay time. So now here next rise time means here from these two, anode current and anode voltage. So here from the 10 percentage to 90 percentage. So this is the case. So now here 10 percentage to the 90 percentage. So this time duration. So this time duration is known as a, so 10 percentage to the 90 percentage of anode current. So time for which anode current is reaches from 10 percentage to the 90 percentage is known as a rise time. And next to anode voltage is reaches from 90 percentage to decreases from 90 percentage to 10 percentage, that is the rise time. So in two definitions. And next here, next case, so this is the delay time and this one is the time. What about the spread time? Spread time means here from the 90 percentage of anode to time taken, time for which the 90 percentage of anode current is reached from increases to 100 percentage of anode current. So that is the spread time. And next here, from the 10 percentage of anode voltage to, so when SCR is on, so that is the spread time. So now here add TD. So now here TD plus TR plus TS. So this is the T on. So turn on. So now here TD plus T on, TD plus TR plus TS. So delay time plus rise time plus, and next spread time, that is turn on characteristics. Sum of delay time, turn on time and spread time is known as a turn on time. Next, what about the turn off characteristics? Turn off characteristics means here, so when you turn off when you apply reverse potential, so thyristor will not turn off immediately, it will decreases linearly like this, it reaches to 0 and current is negative and this is the maximum value. So now here gate recovery time means here, so here there may be a charges J1, J2, J3. So here, so there may be a charges to remove that J1 and J3 junction charge carriers. So the time taken to remove J1, J3 junctions charge carriers, so that time duration is known as a, so that is TRR, reverse recovery time. And next to remove that J2 junction charge carriers, so that is the gate recovery. So it is connected to the gate. So to remove the J2 junction charge carriers, time taken for that is the gate recovery time. So now TRR plus and TG equals to, so that is the circuit turn off time. So now here this is T on, this is T off. So now here third question. So illustrate the switching characteristics of BJT indicating clearly turn on and turn off. So if you see the diagram here, these are the turn on and turn off characteristics. So here TD and TR. So in the SCR case there is a TS, spread time. There is no spread time here, only TD and TR. Here how many TS, and here another one is a delay time and fall time. So this is a TS, not TS, TD. Delay time, TD and TS. So now here we are giving initially negative supply, negative base voltage, the instance, so TD time, so when it will be turn on, so this duration is a delay time and this duration is a turn on time. So now here, so from this collector current reaches to this 10 percentage of collector current, and collector emitter voltage reaches from 100% to this 90%. That time is known as a delay time. And next, what about the rise time? Means from the 10% to 90% and from the 90% to 10% decreasing here. So that is the rise time. And next, what about the delay time? Delay time, same fashion here. So if you see this one, delay time means here VBE reaches from maximum value to this 90%, and next here collector current IC from 100% to 90%, and next here VCE turn on to, and next here 10%. That is delayed time. And next, turn off time means here, turn off time means here, sorry, fall time means here from the 90% to this 0 and 90% to this 10% and this 10% to this 90%. That is the fall time. TS plus TD plus TF equals to, that is turn off time. Next, fourth one, explain the operation of IGBT with insulated gate bipolar transistor with its structure, with basic structure. What is the structure here? This is the structure of a IGBT. IGBT. Here, how many terminals here? So here, gate, collector, emitter. So it is having, so this is the gate, collector, this is the gate, emitter and collector. How many layers? 4 layers. So here, so first P plus layer and again N minus layer and again P plus layer and again N plus layer. These are the metals and this is a SiO2 layer. Gate is connected to SiO2 layer and emitter is connected to this metal and collector is also connected to the metal. And now here this layer is the injecting layer. Holes are injected into the N minus layer, and next this is the drift layer, N minus layer. Here it is a body layer and N plus layer is a SiO2 layer. So now here this is the construction of IGBT. So now here, this is the positive, this is the negative. So collector is more positive with respect to the emitter. What will happen? So here this J1, J2 and J3. J2 is in reverse bias and J1 is in forward bias. So there is no current flows from collector to emitter. So here again positive and this is negative. Gate is positive with respect to emitter. So here it acts as a capacitor and here SiO2 layer acts as a capacitor. One junction is formed, one layer, one channel is induced here. So here electrons flows from one channel will be induced. Electrons flows from N plus layer to P plus layer, N minus layer and P plus. And electrons current and current direction is always opposite direction. So now here these are the layers and here, so current is flowing from collector, P plus layer, N minus layer, P, N and this emitter. So electrons flows from this N plus, P, N minus and P. So these are the electrons direction and this is the current direction. And next here, fifth question, turn on methods of SCR. How many methods? So here till now we have seen only gate turn on method. So first one is the forward voltage triggering, thermal triggering, that is temperature triggering, dV by dt triggering, radiation means that is light triggering and gate triggering. So gate triggering already we discussed, and next forward voltage triggering. So this is the structure of SCR: anode, cathode and gate. So J1, J2, J3 junctions, P1, P2, P3, P4. When anode is positive with respect to the cathode, so here J1 is in forward bias and this is in forward bias and J2 is in reverse bias. So here only thing is, so this is the VAK. So now here breakover voltage. So now here VBO is greater than VAK. So now here this VBO is greater than VAK. This J2 junction is in forward bias. So J1, J2, J3 in forward bias means here current will flow from anode to the cathode. So SCR will conduct. So SCR will be turned on, that is a short circuited. So this is the VBO is greater than VAK case. And next thermal protection means here same. Here thermal protection means here some amount of temperature is applied here. So here J2 junction is from reverse bias to the forward bias. And next here this is in, so increasing temperature at gate. So now here this SCR will be turned on. And next dV by dt, there may be some internal capacitances. So here what will happen, dV by dt, because of this dV by dt, sudden increase in voltage, so what will happen, C equals to I, so I equals to C dV by dt. So here because of this sometimes the change in the voltages, sometimes there may be false triggering of SCR. So sudden change in the voltages, there may be false triggering of SCR. So that is dV by dt protection triggering. And next here radiation or lighting triggering means here, so here some amount of light is focused on this J2 junction. So now here this J2 junction is in forward bias. So now again J1, J2, J3 are in forward bias and SCR will conduct. So gate triggering already. So when you give positive, supply is given here, get gate, and now here Ig is greater than 0. So now here again J2 junction is forward bias. In this way, in the 5 methods we can turn on SCR: forward voltage triggering, thermal triggering, that is temperature triggering, and dV by dt triggering, radiation or light triggering, and gate triggering methods. And now here next method, compare the performance characteristics of MOSFET and power BJT. So first, what are the main differences, then I will explain characteristics. So now here, so it is having, so power BJT means here this is the BJT, emitter, collector, base, and now here it is a drain, source, gate. So emitter, collector, base, drain, source, gate. It is a minority carrier device, it is a majority carrier device, it is a bipolar, it is a unipolar, it is a controlled by gate current IB, and it is controlled by VGS, controlled by gate, and voltage control device, it is a current control device. So driving circuit is costly and complex, it is easy and simple and less cost. Switching losses are low, switching losses are high, conduction losses are high and conduction losses are low. Turn on and turn off time is very high and turn on and turn off times are very short, and switching frequency is low and switching frequency is high. So now here another it is a negative temperature coefficient, it is having, it is a positive temperature coefficient. So paralleling of BJT is simple, paralleling of MOSFETs are difficult. This one, it is a simple, and it suffers from secondary breakdown, it is free from secondary breakdown. And thermal runaway is possible, thermal runaway is not possible. Suitable for high power applications, suitable for low power applications, high voltage high current applications, and low voltage low current applications we will use. So these are the applications: UPS, SMPS, static VAR, AC motor control, and AC motor control, switch mode, power supply, SMPS, inverters. And next, input impedance is low, and here input impedance is high. High input current, low input current. Its operating area in the first quadrant, and its operating in the first and fourth quadrant. So now, not performance characteristics means here, these are the performance characteristics. Here turn on and turn off. Here turn on, delay time and rise time. Here turn off, delay, fall time. And next, this delay time reaches to input charges to VGST, from reaches to VGST. So now here up to this one. So here at what time? Here this is the from VGST, from this time to this time. So that is delay time from 0 to this one, VGST, certain threshold value. And next, again, rise time rises from VGSP to sufficient drive voltage or ID current from 0 to full time, is from 0 to full diode current. This is the rise time, this is the turn. TD plus TR means that is turn on time. What about the turn off time? So this duration from VG, from the, it is discharging from the this gate source voltage to this, up to this point. So that is a VGSP. So that is delay time, turn off delay time. And fall time means here, so it during which the input capacitance VGSP to VGST. So this is a VGST. So that is the fall time. So TDF plus TF means that is turn off time. So turn on and turn off characteristics. So this already we discussed. So SCR switching characteristics, same TD plus TR. Classify the commutation circuit. So what do you mean by commutation? So turn off process. So here SCR is a semi-controlled device. Semi-controlled. Turn on is in our hand, but off is not in. We need an external circuit. So that external circuit is a commutation circuit. That external circuit is a commutation circuit. So that commutation circuits are classified into thyristor, forced commutation and natural commutation. If you use the DC supply, so that is forced commutation. If you use the AC supply, that is natural commutation. So now here in this class A, class B, class C, class D and class E, this is external pulse commutation, and this is the voltage commutation, this is the complementary commutation, this is the current commutation, and next this one is the load commutation. So total 5. And next this is the class, this is the natural commutation. So that is class F, class A, class B, class C, class D, class E and class F total. And now here, so interpret the two thyristor model of SCR and derive the expression for anode current. So this is the diagram. So this thyristor PNP, and it is divided into two parts, PNP, and next here is the NPN. So now here the thyristor model. So this is the Q1 and this is the Q2. Let me change the color over here. So this is the Q1 and this one is the Q2. This is the anode, this one is a cathode, and this one is a gate. So now here this is the IA and this is the IK and this one is the IG. And now here this is the IE1. Now here this is the IC1 and now here this is the IC1 and emitter this is the IB1 and now here this is the IC2 and IB2 and now here this is the IE2. So now here IA equals to IE1 and next here IB1 equals to IC2 and next here IE2 equals to IK. So now here another case here. So we know this IC1 equals to alpha into IE1 plus ICBO1 and next IC2 equals to alpha into IE2 plus ICBO2. So we know this formula IC equals to I alpha into IE plus ICBO. So now here we know this formula. So now here this IA equals to IC1 plus IC2. So this one equals to IA anode current equals to IC1 plus this, if you apply KCL, IC1 plus IC2. So now here IC1 means here alpha 1 and this is alpha 2, alpha 1 IE1 plus ICBO1 and next alpha 2 into IE2 plus ICBO2. So now let me change the color over here. So this is how we can write, this is the IA. IE1, sorry, IE1 means here IE1, IE2 means here IK. IE2 means here IK. So now here alpha IA equals to, what is the formula? So IC IE1 plus IE2. So IC2 equals to IC1 plus IC2. Here already we have discussed alpha into IA equals to IC1 plus IA equals to IE1 equals to ICV plus IC1. So now here what are the IK equals to? IK equals to, what is the formula? IG plus this IA equals to IE2 equals to alpha into IA. So plus ICBO1 plus alpha 2. So now here this one equals to IE2 equals IK equals to IA plus IG plus alpha ICBO. So that equals to IA equals to alpha 1 plus alpha IA. This is alpha. So now here alpha 1 plus alpha 2 IA, alpha 2 IG, ICBO 1, ICBO 2. So from this you can write IA equals to, so alpha 2 IG minus ICBO1 minus ICBO2 divided by, plus and 1 minus alpha 1 plus alpha 2. So that is the case. So this is the anode current expression using next, classify various types of gate triggering circuits and explain the operation of RC and UJT. So here there are R triggering, RC triggering and UJT triggering. So here RC triggering explanation and UJT. So here this is the diagram. This is the diagram AC supply and this is the SCR. So here we are giving the anode and cathode. This is the gate. So here we need to give gate triggerings this one. So the limit here, what are the components D1, D2, C and R2. So the limitation of resistance firing circuit can be overcome by RC firing circuit, which provides the firing angle from. So it is from 0 to 180 degrees, but R firing, that is 0 to 90 degrees only. Here this is one advantage. And by changing the phase and amplitude of gate current, so a large variation of firing angle can be used by using this circuit. And now here, by varying this variable resistor, so triggering or firing also can be controlled, that is 0 to 180 degrees in a positive half cycle of the input signal. And next here, during negative half cycle D1 and D2 in forward bias. In the negative half cycle D1 and D2 are in forward bias, and this capacitor charges with lower plate positive through this diode D2, and it reaches to maximum supply voltage, and the voltage remains at maximum value across the capacitor will supply voltage attains 0 across D2 gets the reverse bias. So C will discharges through R2 and D2. And again during the positive half cycle of the input, SCR will become forward bias, and next here the capacitor starts charging through variable resistor, triggering the value of the SCR. And when SCR is charging voltage is equals to gate triggering voltage, the SCR is turned on and the capacitor holds a small voltage value. Therefore, the capacitor voltage is helpful for triggering the SCR after 90 degrees also. This is important. And next here, when in this the D1 diode prevents the negative diode voltage between gate and cathode during the negative half cycle of the input diode D2. So now here this is the circuit for full wave rectifier RC circuit, and now here power can be delivered from the delivered to the load during positive half cycle and negative cycle half cycles because of the full wave bridge. So now here firing angle is 0 to 180. So power is delivered to the load is doubled here. Output voltage is present even the negative half cycle. So this is UJT. So here we are using the Xeno diode RC circuit. This is a UJT circuit. So UJT triggering circuit, this one. Explain the static and dynamic characteristics of SCR. Already we have seen. So this is a forward blocking mode, and this one is a forward conducting mode, and this one is a reverse blocking mode, and J1, J2 are in forward bias, and J3 and here J2 is in reverse bias, and here J1, J2, J3 in forward bias, and here J1, J3 are in reverse bias, and J2 is in forward bias. That already we discussed. So this turn on and turn off. So turn on already we discussed in the first question. This is the turn off, gate recovery time and gate reverse recovery time. So this is the TD plus delay time, rise time and storage time. So that already we discussed. So here these are the delay time, rise time, spread time, all these already we discussed. So now if you see the next question, so here these are the TD. So now here what is the necessity of series and parallel connection of SCRs and the problems associated with this configuration. So why, what is the need when supply voltage is greater than the thyristor voltage? So the device voltage. So that is the case. So the devices, the SCRs are connected in parallel. So voltage rating of supply voltage is greater than voltage rating of SCRs. That is the case. And next here, current rating of SCRs. Current rating of SCRs, uh, supply current rating is greater than the SCR current rating. So for that case also, SCRs are connected in parallel. So what are the problems here? So if two SCRs are connected in series, in series, so what will happen? So though they are manufactured with the same rating, but here from the same leakage current, there are two different voltages, V2 and V1. So VBO1. So one is triggered earlier and another one triggered later. So because of that reason, so unequal voltage distribution across the SCR1 and SCR2. So that is the main problem in series SCRs. So now here same way here SCRs are connected in parallel. So what is the main drawback here? So here for same type of voltage, so there are two voltages, so I1 and I2. So I1 is greater than I2, unequivalent current distribution. So these are the main drawbacks for series and parallel. So now here demonstrate the operation of class A commutation circuit, the function of commutating components. Here this is the SCR. Here this is the forced commutation, this is the load. So now here when it is turned on, we need to turn off. So now here this L and C components are the commutating components. So when you give the, so when it is conducting, so what will happen? The SCR is acts as a short circuit. So if you give the SCR when DC excitation given to the RLC, what will happen? RLC, so that is sine wave. So now here your waveform, the output current waveform is, it looks like this. So now here, so when it is reaches to 0, so now it is going to the negative. When anode current is less than the holding current, so then SCR will be turned off. So that is the case. So by selecting proper value of inductor and capacitor and resistor is a load. So proper value of inductor and capacitor. So we can turn off the SCR in the class A commutation. So now here what about the class B commutation input and output waveforms? So these are the waveforms. So here what are the waveforms? This is the thyristor, main thyristor T1, and this is the T2 means the auxiliary thyristor. This is the capacitor. This is the, what about this one? This is the inductor, and this is the diode, and this is the load and supply. So this is the main thyristor. So this is the class B circuit, commutation circuit. This is the main thyristor gate, and this is the auxiliary thyristor current I0, I0 output current I0, and next here main thyristor current, capacitor voltage, and IC current. So capacitor current. So here initially what are the assumptions? Output current is constant, and here capacitor is initially charged, and now here what will happen? First initially current flows through this one, this is, it reaches to plus and minus. So what will happen? This SCR is in reverse bias. So now turn on this SCR. So now here this is the case. So here current flows from this in this way, and it charges, and this capacitor is minus and plus, and it will be turned off. Reverse potential is applied across this auxiliary thyristor. This is minus and plus means this is again diode is turned on, current is flowing through this one. So it will not go in this way, it will go in this way. It reduces the anode current of this thyristor, and here anode current is less than the holding current, it will be turned off. So these are the waveforms. Output current is constant. So output, this is the main thyristor current is also constant. So this supply, this is the capacitor voltage and capacitor current is initially charges. So now here when main thyristor is done on, this capacitor voltage decreases, and next here current is in reverse direction, maximum value. And now these are the waveforms for class B commutation circuits. And next, class C commutation circuits are here. So here in the class C commutation, these are the waveforms. So IG1, IG2, IT1, IT2. So this is T1, this is T2, and this is C. VT1 and VT2, IG1, IG2, and this is the IG1. And now here IT2, IT1 and IT2, and VC, and this is a IC. So here it is a complementary commutation circuit. So when T1 is on, so now here how it will turn off. So now here initially when T1 is on, current flows in this, and again current flows in this, again in this way. And now here when you turn on TA, and this is a plus and this is minus. So now here this is plus and minus and plus, and now here we are applying reverse potential to this one, it will be turned off. And again to turn off this one, so now here this is minus and this is plus, it will be turned off. So T1 will be turned off when T2 is turned on, and T2 will be turned off when T1 will be turned off. These are the waveforms for class C commutation circuit. And next, illustrate the class D commutation circuit and function of each commutating components. What are the components here? C, capacitor, inductor, diode, and this is the T1, that is the main thyristor, and this is the auxiliary thyristor, this is the I0 current. And next here, what about this is the main current, and this is the auxiliary current, and this is the capacitor current and capacitor voltage. So now here what will happen here first? So first T1 will be turned off. So now what will happen here? Current will flows from this capacitor and this thyristor in this way. So now here when both the SCR are turned off, so here initially capacitor voltage is supply voltage. So now turn on this SCR, this is a VS. So what will happen here? So now here this is the case. So this is a plus and this is a minus, and this one is plus. This diode will be turned off. Now again turn on this T2, TM, and this is TA. So what will happen? So here what will happen? This TM will be turned off. Again TM will be turned off. That is the case for class D commutation. And explain the R and RC circuits. RC circuit triggering already we have discussed with the need diagram. This is the R circuit triggering method. So this is a G, gate, anode, and cathode. So here R1 is used for to limit the gate current IG, and next the limiting resistor R1 is between anode and gate. This anode and gate. So thyristor limits the gate current not exceeds the peak gate current. So it will. So if gate current is IG, so it will limits the peak value, IG current peak value. It will limits. And next there is resistance limits the current flowing through the gate terminal and its value such that gate current should not be. So if suppose gate current G, so that maximum value, gate current maximum value, it will limit R1, and that is VG, R minimum equals to IG maximum. So this R minimum equals to VG by IG minimum. And next here, what about this R2? Firing angle and output voltage can be controlled by. So this is a firing angle, not this gate current limit. So that is by changing this R2, and R2 is large, then the firing angle will be increases. So if R2 will be low, so the current will be small, and that firing angle will be low. So now here when gate current is applied across the resistance R2, the gate current should be more than the minimum value of gate current, and then only SCR will be turned on. Hence uh, the load current starts flowing through the SCR. And next variable resistor R2 is used to trigger the SCR T1. And next, when R2 value is 0, the firing angle will be minimum. When R2, that firing angle increases with the resistance R. So now here this is the stabilizing resistance. The voltage across the R, this R should not exceed the main gate voltage IVG. So otherwise thyristor will be turned on directly. So ensures that the gate voltage is applied to the SCR. So now here what is the main purpose of diode? It protects the gate drive circuit from the reverse voltage during the negative off cycle of the input, and the diode in the gate circuit prevents the reverse voltage of the SCR during the negative off cycle from the exceeding the peak reverse voltage. And this is the simplest and economical method of triggering circuit, but limited for few applications. So this value is 0 to 90 degrees only. UJT relaxation already we discussed. So now here this is one. Explain string efficiency. So if supply voltage is greater than the voltage rating of SCR, so that is the case SCRs are connected in series. So now here in this case, so now here derating factor formula and efficiency formula. So the supply voltage, and this is the D1 voltage, and N is the number of SCRs are connected in series, and this is the derating factor, and this is the Vs by N into VDS, that is the string efficiency. Now here what about the string efficiency equals to 1 minus D into 100. So now here parallel supply current, so total current is greater than the individual SCR current rating, that is the case SCRs are connected in parallel. So now here what is the formula? Here what is the formula? Same. String efficiency equals to Is by N into ID1. So now here percentage D equals to 1 minus Is into N into ID1 into 100. So that is the case. So now here explain the string efficiency derating factor. So these are the case parallel and series. And now here develop a protection circuit for snubber circuit, means resistor and capacitor. Resistor and capacitors are connected in series, that is the snubber circuit. This is a snubber circuit to protect from the dV by dt protection. So SCR, it is connected across the anode cathode. The last question, identify the requirements of protection circuits to protect the SCR. So how we will calculate the SCR, how we will protect the SCR? First one is so here from the overvolt protection, so here fuse and circuit breaker is used. And next from the over voltage protection, so varistor is used. So here a varistor is a negative voltage current characteristics. If voltage increases, current will decreases. So that is the varistor MOV. So from the over voltage protections, varistor is used. From the over current protection, fuse and circuit breaker will be used. And next here dV by dt protection, di by dt, from the di by dt protection, inductor will be used, and dV by dt protection, from the dV by dt protection, snubber circuit is used. From the temperature here, from the temperature heat sinks we will use, and this is the gate protection. So here Zener diode, what is the main purpose of Zener diode? It will maintains the constant voltage across the gate and cathode, and this is the RG current to limits the gate current, And next here R and C are connected in parallel, so it will minimizes the noise at the gate circuit. This is the protection circuit for this SCR. Over voltage protection, over voltage protection, varistor connected across this one, and fuse and circuit breaker are connected in series with the SCR from the over current protection, and inductor is connected in series with SCR from the DI by dt protection, and snubber circuit, that is a resistor and capacitor, are connected in series. So the from the over dV by dt protection, that is snubber circuit connected across the SCR, heat sinks are provided to, for, at this thyristor. So from the thermal protection, and this is a gate protection. I hope all these 20 questions are clear to you. Question bank discussion. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.